Hello everybody, and welcome to this video that I promised to make for y'all to explain the concepts of optimality of the A star under two conditions. So first, under the condition of admissible heuristics, we would like to see how you can show that A star is optimal. And then the second proof for optimality is under the condition of consistent heuristics. So first, let's talk about the admissible heuristics and prove the optimality of A star. So for this, I want to prove A star is optimal if the heuristic function is admissible. For this proof, what we're going to do is we're going to use proof by contradiction. In proof by contradiction, what we're doing is basically we suppose, or we assume, the wrong assumption or the wrong conclusion, and then what we're going to show is we will show a contradiction. So what we're trying to prove is A star is optimal. So if A star is optimal, then if we find a goal, and what that means is that if A star reaches a goal, then that goal has the lowest cost. Okay? So if A star finds a goal G, then G must have the lowest possible cost. So let's see what does that mean. And what we're going to actually suppose we're proving A star is optimal. So we're basically supposing or assuming that A star not optimal. And then we show that if A star was not optimal, then there would be a contradiction. Then we need to show contradiction. Okay? So let's see what's going on with our proof. First, let's take a look at what is going to happen if we assume that A star is not optimal. If we assume, basically, if A star is not optimal, what that means is that then A star will reach a goal, and I'm going to call this goal G sub 2. And then for G sub 2, f of G sub 2 is going to be greater than f of G if G were an optimal goal. Right? So this is what our assumption of A star being not optimal means. It means that A star will find a G sub 2, a goal, whose cost is greater than another goal that would be an optimal goal. So if I draw the picture of my A star search space, A star search space starts from a starting node, and then it's going to go and expand a bunch of nodes, right? And then at some point in time, it's going to basically encounter in its fringe data structure, or it's in frontier, it's going to encounter a suboptimal goal. So this G sub 2 is my suboptimal goal. Okay, and then what I have here actually is that this suboptimal goal, I'm going to just draw it in red. So this is my suboptimal goal that my A star has reached in its fringe node. And then it will expand it, since it's suboptimal goal and my A star, I assume that it's not optimal, so it would expand it and it would return the suboptimal goal if A star is not optimal. And I want to show that that results in a contradiction. Okay, so to show that, I'm going to actually look at a path to an optimal goal. And let's suppose that on the path to an optimal goal, G, right here, G is my optimal goal, okay? And let's suppose that on the path to an optimal goal, there is a point, a node, that is on the fringe, and my A star has expanded it, and I call that node N. So N, so here's what I'm actually working with. N is a node on path to optimal goal G in the fringe. Okay, G is the optimal goal. Since G is in a goal, therefore h of G must be 0, and therefore f cost of G must be equal to G cost, or cost so far, of G. And finally, I've got my algorithm expand a suboptimal goal, and that suboptimal goal is G sub 2. So G sub 2 is a suboptimal goal reached. As such, h of G sub 2 must be 0. Therefore, f of G sub 2 is equal to G of G sub 2. So these are what I know. From my assumption, I assume that A star is suboptimal, therefore it has reached a G sub 2 goal whose f cost is greater than the f cost of G. So from 1, this assumption tells me that f cost of G sub 2 is going to be greater than f cost of G because G sub 2 is a suboptimal goal. Secondly, I'm looking at the fringe, and one of the nodes on the fringe would be a node N, this green node here, on path to an optimal goal G. But my algorithm has not picked that node to expand, and it has expanded the G sub 2. So from all this, since A star I assume is suboptimal, and its f of G sub 2 is greater than f of G, I know that to have been expanded from the assumption, so from assumption, f of G sub 2 is going to be considered to be less than f of G sub n because G sub 2 is expanded, right? Because my algorithm has turned a suboptimal goal as a result of expanding G sub 2 before it has expanded n. Now, my contradiction is actually to show that f of n is supposed to be less than f of G sub 2. So, to reach that, we're going to actually do a little work on what is going on here. So, we know that n is a node on path to the fringe. So from this point, we know that f of n, since n is on path to the goal, is essentially equal to g of n plus h of n. So what I'm going to do is that I'm going to add and look at the g of n there. So my heuristic is so let's take a look at this and just keep it on the side, and I will give it just a number. I'll call it number 2. Okay. So I know that heuristic function is admissible. What this means is that if I look at h of n, the h of n is going to be less than h prime of n if h prime of n is the actual cost to g. Okay. Now from this equation, I'm going to add g of n. See the g of n here? I'm going to add g of n to both sides of my equation. From there, I'm going to go and get h of n plus g of n is going to be less than h prime of n plus g of n. I didn't do anything really crazy. I just added g of n to both sides of the equation. Now from this guy, this is familiar. Remember 2? The equation number 2? This is f of n. So this guy is going to be f of n. Okay? Now look at this guy. What is this guy? H prime of n is the actual cost of going from n to g. And if I add to it g of n, which is the cost so far from start to g, the sum of these two is going to be f of g. So the sum of these two guys is going to be f of g. Okay, so I'm going to call this equation equation number 3. Okay, now let's look at equation number 1 and equation number 3 and equation number let's call this equation number 1 plus 1. Okay, so from equation number 1, I gather that f of g2 is greater than f of g because my a star, I'm supposing that it's suboptimal. So the cost of the goal g2 must be greater than the cost of the goal g, because if g2 was the lowest cost goal, my algorithm would be optimal. I'm assuming it's not. From equation number 3, I found out that f of g is already greater than f of n. Right? This is equation number 3 that I got. Now look at this. F of g2, I'm supposing that is greater than f of g. And also I know that f of g is greater than f of g2. From these two equations, I gather that f of g2 must be greater than f of n. Okay? We call this equation equation number 4. But 4 and 1 plus 1, this guy here, these contradict, right? I cannot have f of g sub 2 greater than f of n at the same time when f of g sub 2 is also supposed to be less than f of n. And this is the contradiction that I'm talking about. So if f a star was suboptimal, then f of g sub 2 would be less than f of n. But f of g sub 2 at the same time would have to be also greater than f of n, which is contradiction, which means that a star cannot be suboptimal under a heuristic that is admissible. So if your heuristic is admissible, then A star is going to be optimal. And this is the proof of optimality of A star under tree search under admissible heuristics. All right. Now this second optimality proof would like to prove that A star is optimal for graph search if the heuristic was a consistent heuristic. So I want to show if H is consistent, then A star will be optimal. Now, in order to prove optimality of A star, basically I'm going to prove a slightly different concept here. And then I'll elaborate on how these two will be related. That slightly different concept is that for A star to be optimal, I would have to basically have f of n, or the cost function, the total cost function, which is basically the cost so far of any node, plus the heuristic cost of that node. I want the f of n to be monotonically increasing. Okay? What this means is that if I have a node n, and then I have another node n prime, and then I have another node m, and so on and so forth, to the path to a goal, g, then the f of n needs to be greater than f of n prime, needs to be greater than f of m, needs to be greater than f of g, and so forth. So basically, as you expand nodes, the f cost expands as you go along. This is actually useful because it means that, so if you've got monotonically increasing f cost, so monotonically increasing f cost means that the first goal you reach will have the lowest cost, which then will make A star optimal. Okay, so this is what we are interested in showing, to show that f cost of the nodes is going to be monotonic. Yep, so I'm going to show this. Now, there's a slightly interesting concept here that we need to talk about. Let's suppose that you've got an n node, and then you're basically reaching this node somehow. And let's suppose that this node is a node on a path to goal. We call it G. And let's say that there's another node that's one step away from n, and it's also on the path to the goal. What we want to show is that the f prime, or the f cost for n and n prime, are monotonically in an increasing order. Now, let's suppose that the action that takes me from node n to node n prime, I'll call it C of n, or costs of n, taking action A to go to the node n prime. Then also, I know that the h of n, or kind of heuristic values for going from n to goal, is going to be equal to h of n, and then the heuristic value from going from node n prime to goal is basically h of n prime. Okay? So these are the two things that I know that are the case. Let me delete the prime here to avoid confusion. Alright, so a consistent heuristic means that So H is a consistent heuristic. This means that H of n, according to the triangular equation, is going to be less than H of n prime plus the cost of going from n through an action A to node n prime. This basically is my assumption. This is my assumption that says that my heuristic is consistent. So if my heuristic is consistent, then h of n, this long guy, is less than the sum of c plus h of n prime. So let's look at this equation and let's see what's going to happen with this. If I start with h of n through a consistent heuristic being less than h of n prime plus c of n action n prime, and then if I just add g of n to both sides, okay, so if I just add g of n to both sides, right, I'm going to get h of n plus g of n less than h of n prime through that equation plus c comma n comma a comma n prime plus g of n. Right? So I didn't really do anything crazy. I just added g of n to both sides of this equation. Okay, so from here, let's see what we have. Right? So this guy is basically g of n, how much it costs to go from start to node to n. So that's g of n. And just give it a different color. Okay, so this is my g of n. Well, that different color didn't really work. And so I've got f of n being less than h of n prime plus c of n action a to node n prime plus g of n. And if you look at this equation here, see g of n is the cost of going from, so g of n is essentially the cost of going from the start to n, right? So that's that cost. Then c is essentially the cost of going from n to n prime, so that's that cost. And then h of n prime is the cost of going from n prime to g, or to your goal. So h of n prime is essentially the cost of going to the goal. So if you add these three to each other, you're going to get f of n prime. So from this equation now, what we deduce is that your f of n, which is one step before n prime, is going to be less than f of n prime, which is exactly what I wanted to show there. So f of n, which is one step before n prime, is going to be less than f of n prime, which is one step after n. So since f of n is basically increasing monotonically, meaning that it keeps increasing, it never stops or get decreasing. So since f monotonically increases, if A star finds a goal G sub 1 before it reaches another goal, G sub 2, f of G sub 1 is going to be less than f of G sub 2, which then makes A star optimal. Okay, just a slight catch that if there was another node before n that you have reached, it would have lower cost than n that you have reached because of the consistency in your heuristic. And this is the proof that A star is optimal under considering consistent heuristics. All right, well, I hope this helps you all understanding the concept, and hopefully you will study, and good luck with your midterm.